Good morning. I'd like to discuss some ideas revolving around the absolute scale of the universe, or its appearance at the largest scales. And I also want to talk about two major theories about the shape of the universe, one of which, because of its popularity, is generally viewed as correct, and the other, which, because it is generally misrepresented, is considered incorrect. But first, let's take a look at some of the stuff we know because we've looked. You'll see I have here on the screen the beginning of a Wikipedia article about the Sloan Digital Sky Survey. Here is a common image of the SDSS, Sloan Digital Sky Survey. It shows the galaxies in the universe out to a redshift of 0.15 on a single plane. That single plane has been growing over the years. In 2000 through 2005, they imaged 8,000 square degrees of sky in 5 optical band passes. So let's think for a moment about what proportion of the sphere that is. The area of a sphere is about 4 times the area of a circle with the same radius. So the area of a unit circle, if you said r equals 1, the area would be equal to pi, and the area of the sphere with a radius of 1 would be equal to 4 pi. The surface area would be 4 pi. So, how many square degrees are in a circle? Well, I wish I could explain this better at this moment, but I'm in such a hurry to get to the answer, I'm just going to turn this into a unit conversion problem. I'm going to make this statement that the total solid angle exposed to a point in space, like this one, is 4 pi square radians, which is also called a steradian. And to convert that into square degrees, what I'm going to do is say that there are pi radians in 180 degrees, and I'm going to square that so that I will cancel out steradian and square radians. So we will get 41, let's just round it to 41,000 square degrees. So during its first phase of operations, in 2000 to 2005, the Sloan Digital Sky Survey imaged more than 8,000 square degrees of sky. So 8,000 divided by 41,000 is almost 20% of the sky. They went on in 2005 to 2008, mapping the structure and stellar makeup of the Milky Way. So that would be a very nearby stars. That would mean if this was the survey of stars in 2000 to 2005, and then they started mapping stars in the galaxy, all of those stars would appear right here, right at the very center of that, because all of the stars that they're mapping is inside the Milky Way. And that may also be part of the reason that this area is blank, because if the Milky Way is going like that, then we would pretty much be blocked from viewing this angle or this angle by the structure of the Milky Way. Then in mid-2008, SDS-3 was started. It comprises 4 separate surveys, each conducted on the same 2.5 meter telescope. And then in still during that time, in 2011, they apparently started the APO Galactic Evolution Experiment with high-resolution, high signal-to-noise infrared spectroscopy to penetrate the dust that obscures the inner galaxy. So if we're penetrating the dust that goes through the inner galaxy, we should be able to start getting some kind of reading of what's out in these directions that are straight through the dust of our galaxy. Here we go into the future, because it's 2015 now, and it's extending the precision cosmological measurements to a critically early phase of cosmic history. What does that mean? That means essentially they're going to try to extend this range out further so that they can see further out. Because essentially this is further into cosmic history. There's a video out on YouTube from the Mars Underground that shows the Sloan Digital Sky Survey in animation. So what they're doing is actually going backwards from the Earth, going backwards, looking deeper and deeper into space in this. And this, I think, shows how it was in... wow, this is just completed after June 2005. So this is from their original set of data. They've collected a lot more since then. But that original set of data mapped 20% of the sky out to a redshift of about 0.15. All of the galaxies in here are mapped according to their redshift, and you can see kind of planes. It looks like it'll start to spin here in a second, and you'll be able to see individual planes of view where they took. These are the regions basically where they pointed their telescope for long enough to get the resolution that they needed to collect the data. So you can kind of see that it is not just a two-dimensional surface, but several planes of view. Now at the end of this video they start backing off. You can see kind of an idea of how far their survey went out. It went out just they feel confident in their data out to about a redshift of 0.15. Out beyond that, they do have some things that they saw, but they weren't necessarily confident enough of the things. And then superimposed on that, this is not part of the Sloan Digital Sky Survey, but this map here is the cosmic microwave background radiation. Now, I believe what they are essentially saying is that this is a redshift of 0.15. That would be about this. That would be about the proportion of velocity of an outgoing piece of matter compared to something that was going at the speed of light. So this outer sphere is essentially the limitation of the speed of light in 13.7 billion light years. This inner part is how fast something with a redshift of about 0.15 would be. Now in contrast, there is another survey that is called the Hubble Deep Field Survey. Whereas the original SDSS covered about 20% of the sky going outward, this is, oh dear, that's a bad way to show it. 20% of the sky. To describe 20% of the night sky, I will use this picture from Chris Kotsiopoulos. Just a region something like that, but taking up 20% of the surface area of that entire global celestial sphere. So that's SDSS, and that's probably not nearly 20% what I'm showing there. This whole region that is shown here might be probably doesn't even make up 20% of the whole night sky. This is just a small portion of the night sky shown in this picture. It's a very pretty part. The Hubble Deep Field Survey, on the other hand, focuses in on an area that is 2.5 arcseconds by 2.5 arcseconds. My apologies for writing on this beautiful picture. But not arcseconds, I'm sorry, arcminutes. The resolution of the human eye, when you go out to see an eye chart, when you get down the eye chart until it gets to the point where it is 20/20 vision, and you look at the letter E, then 2.5 degrees is the size basically is about half the height of that letter E. I'm sorry, 2.5 arcminutes is about half the size of the letter E on the eye chart from wherever you're sitting when you're being measured for your vision. And that is the size of the Hubble Deep Field Survey, a small region in the constellation Ursa Major. And as luck would have it, commons.wikimedia.org has a picture of exactly where the Hubble Deep Field is relative to the constellation of Ursa Major, though there are no pages that link to this site. It was uploaded by World Traveler. While I'm trying to credit him, it looks like he actually does not wish to be known that much. Now, I like this video on the Hubble Deep Field, which is calls it the most important image ever taken, or perhaps the most impressive image ever taken. I'm not sure what IMP stands for. But you can see in this video, he kind of zooms into the galaxy, and then he zooms... Oh yeah, here we go. Alright, let's check the accuracy of this video. Here is Orion. Here is the Big Dipper. And so, from the image I was looking at before, looks like the location of the Hubble Deep Field Survey should be right there. And in here, they've got Orion right here, and let's see where they zoom in. They're going to go... Oh, did I pick the wrong spot in the video? Maybe it's... Oh, they transitioned to a different point in space. First of all, no, there's Orion right there. And where are they going? Down under his left foot. So I think they missed if they're looking for the Hubble Deep Field Survey, or maybe this is a different Hubble Deep Field Survey. Maybe I was thinking of because there are two, the ultra deep and the deep. Maybe this is Hubble Deep Field South or something like that. Anyway, they start zooming in repeatedly here. There's another zoom in, and I think they zoom in on this again until we get down to that. One of these is a 2.5 by 2.5 arcminute resolution, but they're going to keep going in. Or maybe this is just zooming into different parts of that 2.5 by 2.5. Anyway, okay, I get it now. This image was taken near Ursa Major, near the Big Dipper, but then it was later that they did this image, which was the actual Hubble Deep Field Survey. Probably the same resolution, but this image had an interesting object in the foreground, and it's the most, they said at the time, it was the most detailed observation of a galaxy ever taken. This image, on the other hand, was taken at the same resolution, but with no interesting object in the foreground, so that you could see a whole lot of galaxies in the background. Now there's a part of this video that I want to see if I can find out anything more about, and I'm going to play that little part of the video with sound.
Big to get our heads around. Our brains just aren't wired to visualize big numbers like 47 billion. That's the size of the universe, 47 billion light years in radius.
So, he says that the universe is 47 billion light years in radius. Now, that can be compared to the universe being 13.7 billion light years old. Or not light years, but years. The trouble is, if you ask various astronomers how far across is the universe, no one is going to give you the same answer. According to that chunk of the video I just showed, it is 40 billion light years in radius. I've never heard a number that big anywhere else. In general, Hubble's law is used as an estimation for the size of the universe. The assumption is that the maximum distance is equal to the speed of light times the age of the universe. So the actual maximum amount is speed of light times 13.7 billion years. Or just interchanging light, you just stick that over there and you get 13.7 billion light years. Now, how can I describe the two essential concepts? There's a stretchy space concept and a Big Bang concept. The stretchy space concept has co-opted the name Big Bang, so you can no longer discuss the Big Bang concept with any clarity. That's the way it's been my whole life. Nothing has really changed. But you can see the essence of the debate in the now out-of-print book called Relativity, Gravitation, and Cosmology by Edward Arthur Milne in 1935. Here is the essence of Milne model cosmology, that the Big Bang really was a Big Bang. All of the universe began at a single point in space, at a single point in time, and radiated outward at the speed of light. He predicted that you would find a roughly homogeneous distribution at the center, getting younger but denser as you looked out. You may notice the obvious effect that this doesn't appear homogeneous. Things must surely look very different from the point of view of this blue dot here than from the point of view of this red dot here. However, if you actually do something called a Lorentz Transformation on this animation, so as to view the events from the point of view of this blue dot, you'll find something as you. Right now, the red dot is stationary and the blue dot is moving near the speed of light. That, in a space-time diagram, that would be represented by one of these diagonal lines. What the Lorentz transformation does is takes those lines that are near the speed of light, this diagonal line in the space-time diagram, and maps them to a vertical line, like that. It doesn't stay there, but what I want to do is, and it takes every event in space and time and moves it to another position in space and time, so we can look at things from the perspective where, for instance, instead of the red dot being stationary, the blue dot is stationary. So I actually have had that done already so that I can look at what it looks like from the blue perspective just by typing that in. Now you can see that the blue dot is at the center of the map. The red dot is just barely visible behind this cluster of galaxies over here. There it is. And the distribution of galaxies in the figure looks essentially as it did before. What Milne argued for was that the universe was isotropic from all perspectives, but it was not homogeneous. Quite the contrary, the universe tended towards infinite density at the very edges. However, it appeared this way from all points of view. People didn't like Milne's model, so far as I can tell, not for empirical reasons, but simply because they either didn't understand it or didn't want to understand it. One famous book by P.J.E. Peebles rejects Milne's model simply on the basis that he doesn't think it's very interesting. Usually scientific models are judged on the merits of something called Occam's razor. Among competing hypotheses, the one with the fewest assumptions should be selected. The fact that Milne's model is uninteresting is actually a strong point in its favor. All Milne's model assumes is 1. The validity of the Lorentz transformation, and 2. That the observations of redshift represent actual Doppler shift. The Standard Cosmological Model, on the other hand, goes in an entirely different direction. First and foremost, the Big Bang is not really a Big Bang. Instead, we have a uniform and infinite distribution of particles starting not together at a point at the beginning of time, but rather already distributed at time zero, the beginning of time. And in the Standard Cosmological Model, there's a visible part of the universe, and then you've got the whole universe. Because the universe is 13.7 billion light-years old, it stands to reason that the furthest things in the universe that we can see is 13.7 billion light-years away. However, if we wait a billion years from now, the images from the primordial universe out here will begin to reach us. So according to the Standard Cosmological Model, we're constantly seeing new features come into view over time. Now, I used to argue that this idea was ridiculous, stupid, silly, absurd. But I no longer think that. Quite the contrary, whether this idea is correct or incorrect, it should be modeled as carefully as possible and compared with the empirical evidence. The fact is that with what we've observed so far between the Sloan Digital Survey and the cosmic microwave background radiation, and the Hubble Deep Field Survey that just goes out in just a couple of little points, there would be no measurable distinction between the Milne model and the Standard Cosmological Model. They both predict a perfectly uniform distribution of matter in this region here, where the Sloan Digital Survey has done most of its work. Both predict this low-frequency radiation coming in from all sides, from the edge of, basically the edge of the observable universe. Now, what I'm going to be looking for over the next few years as the data comes out is a distribution that looks something like this. We're going to have a Big Bang and a secondary Big Bang, with an inner part of the universe that is 13.7 billion light-years in diameter, and an outer part of the universe that is much bigger and older. I suspect that the dipole anisotropy in the cosmic microwave radiation will be lined up with this vector here, where this is the center of the original explosion, and this is the center of the secondary explosion that is 13.7 billion light-years across. Half of that radius, 13.7 billion divided by 2, is somewhere around 7 billion light-years in radius. The scale of the Sloan Digital Sky Survey just covers a tiny not really a tiny region, a good portion of this. If this model is correct, then well beyond the Digital Sky Survey, I would predict a statistically significant peak in supernova explosions in the region around 7 billion light-years away, and an asymmetry in the distribution of galaxies in the region beyond 7 billion light-years away. And my expectation is that that asymmetry will line up with the dipole anisotropy of the cosmic microwave background radiation. I know that the standard explanation of the dipole anisotropy is that it is the Doppler shift due to the sun's motion around the galactic center. But these calculations always start by assuming that the cosmic background radiation is emanating from a stationary surface. What I would like to do is repeat this sort of calculation under the assumption that the cosmic background radiation is emanating from a surface that is moving away at nearly the speed of light. Now, I've been making this argument for years, since before I got my MS degree in physics and before I got my MS degree in math, that Milne's model is actually correct and the Standard Cosmological Model is wrong. I realize now that may be too much of a big pill to swallow all at once, but I do wish that at least the Milne model would stop being treated as a primitive, flawed version of the more advanced and correct logical model. it's a completely different model, which just happens to make very similar observational predictions. When Galileo compared the heliocentric model of Copernicus to the geocentric model of Ptolemy, he did not argue his case by saying geocentric actually means heliocentric. He said these are really two different models, and one is right and the other is wrong. So why do we happily go along with people who say the Big Bang isn't really a Big Bang? They're missing the point that there really is a Big Bang theory, and it is totally different from what is the generally accepted Standard Cosmological Model. Well, thank you so much for watching. What do you think? Forward this video on to somebody that you think may know more than me, and see what they think.